Now we'll discuss how to analyze the motion of rolling with a sliding. We already studied in the previous article that whenever there exists sliding with rolling, kinetic friction acts on body. And kinetic friction acts, that means V is not equal to R omega if V is the translational speed and omega is the angular speed about center. And two cases are framed for the situation. One is V more than R omega and the other V less than R omega. Now for the two situations, we can have some specified methods to analyze different kind of numerical problems. Let's discuss the situation when no external force is acting on a body. So if we talk about when F external is equal to 0, and if we talk about our first case when V is more than R omega. So let's see how we can analyze the situation, and let's handle a simple problem in a specified manner. Like there's a rough surface with the coefficient of friction mu, and a body is placed on this rough surface. Say this is a round shaped body having moment of inertia I, and suddenly a translational speed V0 is supplied to it without any rotational speed. So this is the situation V is more than R omega because initial translational velocity is V0 and no angular speed is given, so V is more than R omega. Obviously in this situation the point of contact will move translationally in forward direction, so it will experience the friction in backward direction. And here this kinetic friction we can write as mu mg because the normal contact force will be balancing the weight of this body. And due to this friction, this translational speed will decrease because it is opposing, and the torque provided by this friction will impart some angular speed which will increase due to the torque. And say at t equal to 0 we have just placed the body and imparted an impulse due to which it started moving at a speed v0. And say we analyze the motion after time t. One, we can state the body is having some decreased linear speed Vf and some increased angular speed omega f such that Vf is equals to R omega f. So as no external force is present and if Vf is R omega f, after this point onward we can write the friction is equals to 0. Up to this point the body was experiencing the friction mu mg. So if we say wish to find the time after which the body will start pure rolling, because now onward we can say the motion will be pure rolling. Say we are required to find the time, the translational and angular speed when the body will start pure rolling, or the distance traveled by the body in this period. So all such things we can very easily analyze by writing impulse momentum equations. If we write impulse equation for motion of the body, we can say that initial momentum of body was mv0. The friction acted for a time t in opposite direction, so I can write minus mu mgt, the impulse imparted on the body in opposite direction, which is product of force and the time. And this must be equals to mv final. Say this is our equation 1. For rotational motion, if I talk this for translational motion, for rotational motion, obviously as no angular momentum was there, initial angular momentum I can use as 0, and the torque applied due to friction will be mu mg r if r is the radius of this body, and this torque is also acting for the period 0 to t. So we can add the angular impulse which is mu mg r into t, which is equal to the final angular momentum of body about the center, which can be written as I omega f, and omega f, as it is pure rolling, we can write as Vf by R, which is our equation number 2. Now from these two equations, if we carefully have a look, if we substitute the value of mu mgt here, like this R I can cancel and square it. I am just taking this radius term on the other side of equality, and if I add the two equations, this mu mgt gets cancelled out. It is mv naught is equals to m plus I by R square into Vf. So in this situation, I can see the final speed with which the body is translating at the time of pure rolling will start can be written as mv naught by m plus I by R square. This is the way how we find out the final speed. If I substitute the final speed over here, I'll get the time when the pure rolling will start. Similarly, if I wish to calculate the displacement of body for the time it was in rolling with the sliding, so this can also be easily calculated by speed equations. As the acceleration of body we can write as minus mu g, because the friction is acting opposite to velocity and the acceleration will be friction by mass, that is minus mu g. So the time t in the beginning of which the speed of body was v naught, and if it has traveled a distance s in same direction, which is the displacement covered by the body during its motion of rolling with the sliding, this s can be easily calculated as v naught t minus half mu g t square, and as we already calculated the value of t, we can get the displacement also. This is the way how we can easily analyze all the parameters related to this motion. Say if we similarly analyze our second case analytically, which was a situation when v is less than r omega, where we can state on a rough surface. I'm just taking up a situation which can be handled mathematically. For a rough surface with friction coefficient mu, we have placed the body in such a way that initially it was spun at an angular speed omega naught, and it was dropped gently on the surface and was not imparted any translational velocity along the surface. So due to this rotational motion, we can say that the point of contact at the bottom will be sliding in backward direction with the speed r omega naught, due to which the friction will act on it in forward direction. And again, if the coefficient is mu, the friction can again be written as mu mg, because in this situation the normal contact force will be balancing the weight of the body. Now due to this friction, obviously the body will gain some translational speed, and the torque due to friction, we can see it is in the direction opposite to the angular speed, so it will decrease the angular speed to omega. Say this was the time t equal to 0 when the body was spun and placed on the rough surface. And if we talk about the parameters of motion, that is final speed Vf, angular speed omega f, and the time t when pure rolling will start. In this situation, we can state if finally Vf is equals to r omega f, again we can write impulse equations as, if we write impulse equation, we can state for translational motion its initial momentum was 0. So whichever momentum it is gaining is due to the force of friction, which can be written as mu mgt, and this equals to mv final. This say our equation 1. And for rotational motion, initially it was having some angular momentum I omega naught, and the torque of friction is opposing it for the time t. So I can write it minus mu mgr t is equals to finally it is I omega final, which can be written as Vf by R. As now after time t pure rolling will start, and here friction becomes 0 as no external force is present. Here, if I just have a look, this r if I cancel out, this will be divided and this will be r square. Now, if I add the two equations, I can see this term will cancel out and it will be I omega naught by r is equals to m plus I by r square into Vf. You can see we are getting the final speed of body when pure rolling will start, which is I omega naught by r into m plus I by r square. This is the expression we are getting for various kind of object. Very easily you can analyze this, and using this VF, if I substitute it here, I will get the value of time for rolling with a sliding motion, after which pure rolling starts. And if I know the time, certainly I can calculate the displacement covered by the body during the time it was sliding along with rolling. As initial speed is 0, in this situation we can state it as only half et square, and the acceleration of body can again be given as which is caused only due to friction. It can be written as plus mu g. So this can be written as half mu g t square. By substituting the value of time from here, we'll get the displacement. Any other parameter whichever are required in various kind of problems, you can evaluate by using various speed equations if you know the time and the final speed and angular speed using these expressions.